Hi, I'm Darren and welcome to Level Up EE Lab. I'm going to continue working on this pair of 3020 function generators today. Will I be able to get them both working again? Let's find out. During my initial exam of Mr. Brown and Mr. Black, I noticed that the 3 push-button attenuators on each of them were electrically noisy, and that's not an uncommon problem on older gear, and as it turns out, it was pretty easy to clean them. They're conventional push-button switches, and I don't know if this will show up on camera or not, but they're open back here, so getting access to spray in some contact cleaner and cycle them a few times did the trick. I got rid of the noise, but when I was doing my electrical checks, I noticed some kind of bizarre behavior. They weren't performing the way that I expected them to. Now, before I get into the details of that behavior, let's go over to the schematic to see how they're supposed to work and the method that I was using to test them. Here's the output stage. Transistors Q204 and 205 are a push-pull amplifier. Resistors R212 and 213 are emitter degeneration resistors, which connect together here at test point number 9. Then we have R216 and 217 to 100 ohm resistors in parallel. These set the nominal output impedance at 50 ohms, exactly what is specified. Now after that, there are 3 attenuator switches. The out position is a pass-through. The in position routes the signal through a classic pi attenuator network. Now the accuracy of the attenuator resistors is very important. If they are off, I won't get the specified attenuation level, and I may not even get the correct impedance matching, or both. Now here's a dilemma. I can't probe the resistors individually with an ohm meter. They're in various series parallel combos no matter where I put the probes, and I can't measure an individual resistance. So what if I put one probe right here at test point number 9 and the other probe here at the output? Would that work? Well, the answer is yes. That method can give me data that will show everything is working fine. All I need to know is what nominal resistance values to expect for a 10 dB and a 20 dB attenuator, and that's not difficult to figure out. These formulas and this table show what resistor values are needed in a pi attenuator to achieve a particular dB loss for a 50 ohm nominal impedance attenuator. So for 10 dB, you need 96.2 ohms for the shunt resistors and 71.2 ohms for the series resistor. And that's almost exactly what's on the schematic here for R218 through 223 for the 10 dB attenuators. Now imagine that. Now for 20 dB, it's 61.1 and 247.5 ohms, and again, spot on for the schematic values for the 20 dB attenuator. This formula is the resistance across the attenuator, and the values from 1 dB to 20 dB are shown in this column. For 10 dB, it's 51.9 ohms, 20 dB, it's 81.8 ohms. So with all attenuators in bypass mode, I should see 50 ohms. For a single 10 dB attenuator, it is 50 plus 51.9 or 101.9 ohms. For the 20 dB attenuator by itself, it's 50 plus 81.8 or 131.8 ohms. Now to be fair, there is a circuit path going through R209 and 208 to ground through the attenuator shunt resistors, but I can ignore their influence for this purpose because R209 is 27K, which is almost 2 orders of magnitude greater than the resistors I'm working with here, and it will have a negligible effect. Let's check this out now on Mr. Black and see if we get these results. Alright, so here's Mr. Black. I have all 3 attenuator buttons out, which means they're bypassed, and I expect to get 50 ohms when I do my measurements. So let's see what we get. That is not 50 ohms. That's about 600 ohms. And then engaging attenuator A raises it to almost 1200 ohms. Same thing for attenuator B. That's supposed to be 101.9, remember? And then C raises it to 1545, 1550, not 131.8 ohms. So what is going on here? Why is this happening? Well, let me take the meter off here and move Mr. Black around. Hopefully we can get a better view here. If not, I'll do a zoom in camera shot, but all these resistors in here, the attenuator resistors and R216 and R217 have been modified. 216 and 217, they're not 100 ohms each, they're 1.2K. Put two of those in parallel, 600 ohms. And then all the resistors over here, the ones for the attenuators, have also been modified. R218 should be about 71.2 ohms. It's actually 845 ohms based on its color bands, and 219 and 220 should be around 96.2. They're actually 1.15K ohms based on their color bands. So what gives here? Well, what has happened clearly, now that I see this evidence, is somebody has modified Mr. Black to have 600 ohms output impedance, not 50. Jumping back to my spreadsheet, these columns show the resistors needed for a 600 ohm nominal impedance attenuator. So for 10 dB, 1155 ohms for the shunt resistors is needed, and Mr. Black has 1.15K, and 853.8 ohms is needed for the series resistor. Mr. Black has 845 ohms, and we can see a similar match for the 20 dB attenuator. Now the calculations for the resistance from points 1 to 2 needs to be updated, and I've done that here, so I expect to see 1,223 ohms when a 10 dB attenuator is engaged, and recall I saw 1,200 ohms, and then 1,582 ohms when the 20 dB attenuator is engaged, and I saw 1,550 ohms. So folks, Mr. Black doesn't have a 50 ohm output impedance. It clearly has a 600 ohm output impedance. There's nothing intrinsically bad about all this. In fact, 600 ohms is more convenient for working with audio gear, whereas 50 ohms is more so for RF gear. It's just confusing because the front panel clearly says 50 ohms. And I suppose if this was a personal test lab and you knew what you had and didn't care, it'd be fine. But sure is confusing when someone like me buys this at a Hamfest, and if I didn't catch that and started using this, well, I might get some wacky results in my measurements, and there'd be no evidence without digging into this level to figure out what's going on. It's also obvious at this point when I look at the solder joints here, and hopefully this shows up on camera, but there's residual solder flux all over those connections where those resistors were replaced. What could I do at this point? Well, I could easily revert it back, just remove the resistors and put in correct ones and restore it to 50 ohms, but there's no pressing reason to do so right now. What's here is correct for 600 ohms rather, and it's working very well, so I'm just going to leave it alone. And one final observation, there was an additional modification here. There's a piece of jumper wire that's shorting across resistor R202. And if you jump back to the schematic, that sets the low limit on the amplitude pot. So without that shorted and you turn this down to full counterclockwise, you will still get some signal going into the final amp. With this shorted to ground now, you'll get 0. So maybe they wanted this control to be able to dial the output completely down to 0. Either way, that's another thing that I'm just going to leave alone. Now, what's the story with Mr. Brown? Has it been modified? Well, looking at the component side and the solder side, definitely don't see any clues there. And I've got it connected up to the DMM with none of the attenuators engaged, and I'm getting 50 ohms. So far, so good. Let's check out the first attenuator, which should be 10 dB. We're getting 102.8 and expect to get 101.9, so looking good so far. This should also be the same, and it's not, 132.8. I expected 101.9 also, so that's weird. How about the 20 dB attenuator? Okay, that one looks correct, 133.1, expected 131.8, but why is the second 10 acting like a 20? In other words, instead of going 10, 10, 20, it's going 10, 20, 20. Well, here's another little tiny thing that I missed. Look here on this front panel. Look how it's labeled. Minus 10, minus 20, minus 20. This is a little sticker that's on there, and that's quasi-professional, so this might have been the way that this unit left the factory with a slightly modified step attenuator. Now, just like with Mr. Black, this isn't causing any harm. I'm just going to leave that alone as well. There's a simple lesson to be learned here when working on vintage gear. You always want to cross-check the schematic with the bill of material and any other information in the manuals with the actual hardware that you're working on, because in my case, I found some discrepancies and it was best to fix those now rather than to catch them later when, let's say, I'm trying to test a circuit and I'm not getting results that make sense. Now, before I started this episode, I did go through and address all the noisy potentiometers in each unit. And the way that I do this, I remove them from the chassis, remove them from the circuit, and then clean them and lubricate them and check them out on my analog vacuum tube voltmeter. They all look fine now, so I put them back in and reconnected them. And I suppose I could have gone through shotgun approach on both units and cleaned and relubed them all, but in this case, I don't think it's worth the time and effort to do that. I'm really just trying to focus on what's definitely wrong here or likely to fail in the near future. And if they're fine now, they're likely to stay fine. But even if they're not, it's not that much work later to go in and fix them one by one versus spending a few hours and doing all of them. Moving on, I have received all the parts that I need to repair the power supply in Mr. Brown. So that'll be what I'm working on next. Now, I also have all of the electrolytics that I might need for both units, and if I do get both of these working fine, I'm going to take the time to replace all the electrolytics. Now, I just got done saying I wasn't going to spend the time to recondition all the potentiometers, so why am I going to spend the time to replace electrolytics? Well, my rationale is if a pot starts to get noisy, it's not going to hurt the unit. Yes, it will take some time to repair it, but if electrolytic goes bad, the circuit, best case, may just completely stop working, or worst case, the cap may explode or leak electrolyte, and that can actually cause damage to the circuit. So I just don't think it's worthwhile to keep these old electrolytics in, especially when I already have evidence that one of them had gone bad. Jumping ahead a few hours, I have finished replacing all 10 of the electrolytic capacitors in the power supply section on Mr. Brown, and good news, it is working normally now. So that definitely fixed the problem that I was seeing in the last episode with that capacitor leakage causing AC ripple to leak through the whole circuit. So back to normal now. That's great. Now I still have 2 more 10 mics and a couple more 47 mics elsewhere on the board. I'll replace those next, but I did want to replace the ones that were in the power supply first to make sure that the whole unit was going to work, and so it is. That's great news. Just a quick couple of comments about the caps that I chose. For C18 and C19, and these are extra parts here. These will be for Mr. Black next, but for C18 and C19, I went with 1000 mic, same value that's in the stock rig, but I upped the voltage to 35 volts. Now, for some reason, the stock ones were rated for 25, which is odd because the nominal DC voltage in that part of the circuit is only a volt or 2 below that. There's essentially no headroom with 25 volt rated cap. So 35 gives a much more comfortable margin. The second batch here are the 10 mic 35 volts. I replaced them with the same rating. But I chose Rubycon Series TWL, which is a low leakage design, only because the parts list specify they're supposed to be low leakage electrolytics. Don't know what low enough is, but I just went with a generic low leakage capacitor. And speaking of that, the 47 mic 10 volt parts that are elsewhere in the circuit are also low leakage. Here I went with the Nichicon's UKL series there. And I will put in the description section of this video the exact part numbers that I chose in case you're ever repairing one of your own versions in the future. And just to show that the power supply is working well, I've got trace number 1 here. That would be the yellow trace up there, set for probing the various spots on the power supply. So let's start over here.
This item contains hazardous voltage and safety precautions must be followed. If you're following along and working on your own version, you're doing so at your own risk.
That should be minus 15 volts. That looks good. Plus 15 looks good. It's 5 volts per division on the yellow trace. And then over here, if I remember which one is which, nope, that is not it. There we go. That's plus 5 volts. Looks nice and smooth. And minus 5 volts. Also nice and smooth. So definitely looking a lot better than it did with the old caps in there. And here they are. Here are the ones that I replaced just for reference. Now, I couldn't resist checking these on my capacitor leakage tester, because other than the one large cap that had the obvious leaking electrolyte, there wasn't anything obvious on the outsides of any of these other, but nevertheless, 3 out of 6 of the 10 microfarad caps checked bad on the capacitor leakage tester. They had leak rates that were an order of magnitude or two worse than a new cap, so definitely time to replace them. The 47s, the 47 mics checked okay, but still not batting 1,000 here for good caps in this old, decades old product. So certainly it was time to replace all the capacitors, all the electrolytic capacitors, I should say. So next up will be Mr. Black, and on him also going to replace that overheated resistor. All right, I finished all the parts replacements on Mr. Black, and I'm about to put the back cover back on, but first let's talk about what I found here, starting with the electrolytics. And even though Mr. Black was still working, all of the electrolytics, with the exception of the main filter caps, were bad. And by bad, I mean they wouldn't even register on my leakage tester. And when I checked them on the DMM, the 10 and 47s all measured like 1 to 2 nanofarads instead of 10 microfarad or 47 microfarad. So they're almost open circuit. They were just that bad, except for the main filter caps. Now, for some reason, they check fine when I put them on the DMM, as I'll demonstrate here. I don't have the ability to check their leakage on my leakage tester. It doesn't support that large of a value, so all I can really do is check them on the DMM, and that's 1.049 millifarad if that shows up on camera. So 1,049 microfarad. They're measuring okay, but based on the evidence that all the other caps had gone bad, I replaced them anyway, and you can see them back here. I also replaced a couple of the resistors. Of course, R107, that 75 ohm resistor that was kind of burnt up, and as I was taking it out, the coating flaked off of it, so you can't even read it anymore. Needed to be replaced. And nearby, R108, 330 ohm resistor, and then minus 5 volt supply, and then R106, 10 ohm resistor, and the plus 15 volt supply looked a little toasty, so I replaced those as well. And let me pull this a little closer. You can see the 2 main filter caps. Hopefully here, I know I can't get lighting in here very well. It's really buried, but you can see all the other caps nearby. And back in here is that 75 ohm resistor. And here are the other 2 resistors that are replaced. And with that done, I went ahead and did the calibration procedure. As I mentioned earlier in this series, I was not going to golden screwdriver these. I only made a few minor adjustments for adjusting the calibration of the frequency dial. There were several voltage measurements to be made, and those were all fine. No reason to adjust those. And there was a step in there I skipped. I need an AC distortion meter to make a measurement. I don't have that piece of equipment, so I skipped that. But I had this powered up for maybe an hour or so as I was tinkering around and making my measurements, and I think I know why the circuit board on here ended up looking scorched. There's a lot of heat being generated in this power supply. It is a linear power supply, so it's not going to be very efficient, but we got a combination of the transformer connected to it. We've got a couple of resistors in there, the ones I replaced that are dissipating heat. And we've got on this end here, if we can see it, see at least the screw for it, that's the voltage regulator. That's IC15. That's the 5 volt linear regulator, dissipates a fair amount of heat. So all in all, there's a quite a bit of surprising amount of heat being generated here in this power supply. And because it's enclosed and there's no fan in here, obviously if you leave this guy on for hours and hours on end, I can kind of see why maybe that circuit board is taking the brunt of all that heat being generated right there and ends up discolored. So that might be a caution with this particular model. Leaving it on all day might not be a great idea. But at any rate, I think it's demonstrating that it's working well enough now that I can put the cover back on, and let's check it out and hook it up to the scope and a few other things and give it a look and give it a listen. Okay, I've got Mr. Black all put back together and he's working. I did decide to switch the back cases. I think this looks better, and certainly on Mr. Brown, as I'll show in a minute, the color match is even better there as well. So yeah, the output's working, but it's much more fun to listen to a sweep function generator work than just watch it work. So here we go. And I can also do the sweep as well. Oh yeah, I can have all kinds of fun with this. Okay, and I swapped out the setup here for Mr. Brown, and as I said, these colors match a lot better, so I'm glad I switched the back cases. And just as a quick demonstration here, I thought I'd show something different. If you remember that mysterious extra board that was attached in here, my intuition was right. That's just a tone generator that lets you use the built-in AM modulator without having to put in any kind of signal. And to prove that it's working, right now I've got it set to just over 1 megahertz, and we see the signal on the scope there. My finger in the right spot. Signal on the scope in the background, and I've got one of my really old tube radios here set up, dialed into the frequency, and let me turn on the modulation. And now the signal is going to change here, so I need to slow down the time base quite a bit so we can see it. There we go. And the scope tends to jump around a little bit, but that's okay. And there we go. Tuned into the signal. And you can play around with the amount of modulation, try to get it close to 100%, play around with the carrier level, and so on. So it's pretty neat. I can see where this would be useful for testing out old radios. That's all I've got. Just replacing a few bad capacitors, a few resistors, a little adjustment, and a lot of cleaning, and these two guys are ready for a few more decades of service. Let's hope so. It's always good to repair and restore and keep old equipment working for a few more years. I do recommend that if you find one of these online or at a hamfest, that if it's for a good price, pick it up. It's a great piece of equipment to expand the functionality of any home electronics lab. As always, I hope you guys enjoyed this short little series and are enjoying the content here on my channel. So until next time, bye for now.